Welcome to Caltrans LSIT LS exam preparation course. One aid in your preparation for California licensure examinations. A word of caution, don't use this course as your only preparation. Devise and follow a regular schedule of study which begins months before the test. Work many problems in each area, not just those in this course's workbook, but problems from other sources as well. This course is funded by Caltrans, but you and I owe a profound thanks to others, the course's instructors, from the academic community, the private sector, other public agencies, and from Caltrans as well. We wish you well in your study toward becoming a member of California's professional land surveying community.
Welcome to Unit 3 of the Caltrans LSIT Video Exam Preparation course. For the next couple of hours, we will be discussing basic survey measurements. My name is Jeremy Evans, and I am a land surveyor licensed in California since 1983. I work in the Costa Mesa office of Somas & Associates, where I am the technical manager of the survey department. This unit will serve two purposes. First of all, for those of you studying for the land surveyor in training exam, this unit should prepare you for about 2/3 of the material you will find on the exam. For those of you studying for the land surveyor's exam, the information presented here concerning measurement analysis and error theory will be helpful. There is a second benefit to this tape. The information presented here is a bit dry and not real exciting. This allows you to use this tape as a sure cure for insomnia. Can't sleep? Just pop this tape in the VCR, and I guarantee you that you'll be asleep by the middle of precision versus accuracy. Okay, seriously, again, Philip Kissam, in his book Survey Practice, defines surveying as the art, science, and technology of making such measurements as are necessary to determine the relative positions of points above, on, or beneath the surface of the earth, or to establish such points in a specified position. The key terms in the above definition are art, science, technology, and most importantly to us, measurements. The science and technology of surveying are easy to recognize. The science includes the laws of mathematics and physics that we use every day while making measurements. Technology includes the instrumentation, calculation devices, and mapping technologies, better known as computer-aided drafting and design, or CAD, that have become a necessity in current survey practice. The art of surveying is a little harder to define, but includes the use of judgment gained through experience that allows us to choose the technologies and procedures to do a project correctly and efficiently. Measurements are the cornerstones upon which the surveyor builds his experience. Without a thorough understanding of the basic survey measurements, a surveyor cannot expect to move on to the more complicated technical issues, nor onto the professional issues. This unit of the training program will deal with the basic survey measurements of distance, direction, and elevation. We will also spend time dealing with errors and how they affect our measurements. I would suggest that you take a few minutes now to review the learning objectives and key terms that will be presented in this unit of study. We'll now begin our study of measurements by reviewing the basic principles of measurement. In surveying, we deal with 5 basic types of measurement. They include horizontal angles, indicated by the angle at O, subtended from A to B, horizontal distances, indicated by the lines from O to A, O to B, and A to B, vertical angles, indicated by the angle at O, subtended from A to C, vertical distances, indicated by the line from A to C, and last but not least, slope distances, indicated by the line from O to C. Again, these 5 basic survey measurements that you must understand how to measure or calculate before you can move on to the higher technical issues. In California, the basic units in surveying are feet and hundredths of a foot for linear measurement, or length. This can be horizontal distances, vertical distances, or slope distances. Degrees, minutes, and seconds for angular measure, which includes both horizontal angles and vertical angles. Area is expressed in square feet, or acres, while volume, generally used in excavation, is expressed in cubic yards. Another basic mathematical concept you should be familiar with is significant figures. In recording measurements, an indication of the accuracy attained is the number of digits, or significant figures, recorded. The number of significant figures in any measurement includes the certain, or definite, digits plus one, and only one estimated digit, which is questionable. If a number is recorded as 129.85 feet, as shown here in the sixth numerical value, the measurement has 5 significant figures, of which the first 4 are certain, and the last digit is estimated, making it questionable. In the field, it is important that measurements be recorded with the correct number of significant figures. If fewer significant figures are recorded, then the accuracy is lessened, and the time spent acquiring the data is wasted. Too many significant figures leads to false accuracies and problems with future computations. The number of significant figures is often confused with the number of decimal places. While decimal places may have to be used to maintain the correct number of significant figures, they do not themselves indicate the number of significant figures, as can be seen here in the number 0.000213, which has only 3 significant figures. Exact numbers, such as 5,280 feet in a mile, have an infinite number of significant figures. In survey computations, it is important that calculations be consistent with measured values. Again, we do not want to indicate false accuracies in our answers. In the addition problem shown here, the answer must be rounded to the rightmost column that has significant figures for all the values being added. In other words, the 4 in the value 1.4. The answer must be rounded to the 10th place, since this is the rightmost column that has a significant figure for each value being added. In the multiplication problem shown, the answer must be rounded to the least number of significant figures found in any factor. In this case, the answer must be rounded to 3 significant figures, since this is the number of significant figures in the factor 2.16. At this point, you may want to stop the tape and try the significant figure problems found in your workbook. One last comment about significant figures. It is common practice in survey computations to carry one more digit than is required in the answer and then round to the correct number of significant figures. Measurements can be direct or indirect. Direct measurements are simply that. They are made directly on the ground. They include taping, or measuring a distance with an EDM, measuring an angle with a theodolite, or determining an elevation with a level. On the other hand, indirect measurements involve some type of mathematical computations. Examples include area calculations from measured field data, or intersection calculations like a bearing-bearing intersection used to determine the center of a section in public land surveying. Many indirect measurements are made in surveying, therefore a thorough knowledge of geometry and trigonometry is essential. This brings us to one of the most important and yet most overlooked topics in surveying, the analysis of measurements, more commonly called error theory. Now, don't let the word theory scare you. The analysis of measurements is not that difficult to understand, and the mathematics are relatively simple. You must understand that above everything else a surveyor does, he is an expert in measurement. As a matter of fact, in a court of law, the only area of expertise that a surveyor can testify to is that of measurements. While the surveyor may be the best available source of knowledge on boundary determination, He is not considered an expert on the subject, since the ultimate decision on boundary disputes lies with the court itself. Getting back to measurements, the best way I know to define measurement is to compare it with counting. Counting is an absolute. I have 5 fingers on my hand. I have 32 cents in my pocket. These two values are not approximate values. They are absolutes. Measuring, on the other hand, is an estimate of a value and always contains some error. I can estimate that I am approximately 15 feet from the camera. This distance is an estimate and is obviously not very exact. It does contain error. If I used a tape to measure my distance to the camera, I would get a better estimation of the distance, but it would still be an estimate, and there is still some error in the measurement. No matter how carefully you measure something, it will always be an estimate. Measurements are not exact. All measurements contain some error. Any surveyor who tells you that his measurements are right on really doesn't understand what he is saying. Being an expert in measurement means not only being able to make a measurement in the field or a calculation in the office, but also understanding the quality of the measurement made and being able to determine the equipment and procedures necessary to achieve a required accuracy. Without understanding these basic principles, a surveyor cannot move on to the higher technical issues in surveying. As I mentioned before, all measurements contain some error, and therefore no measurement is exact. Also, the true value of any measurement is never known, and therefore the exact error present is always an unknown. With this in mind, let's look at the formula for determining error. The error in any measurement is equal to the measured or observed value minus the true value. Now, I just stated that the true value is never known, so how can it be used in this equation? Our job as surveyors is to estimate a most probable value for this true value. This most probable value is usually the mean of a series of measurements. We'll get back to most probable values in a few minutes. What I'd like to talk about now is the sources of error in surveying. Natural errors include the effects of wind, temperature, humidity, refraction, gravity, and magnetic declination. An example would be heat waves that cause a target to jump while looking through an instrument on a hot day. Instrumental errors are caused by the imperfections in the construction of a survey instrument. The graduations on the circle of a theodolite may not be spaced evenly, which can cause an error in reading the instrument. Most instrument errors can be eliminated by correct survey procedures, like measuring all angles twice, once with the telescope of the instrument in the direct position, and once with the telescope in the plunged or reversed position. Personal errors arise principally from the limitations of the human senses of sight and touch. Examples include the ability to estimate a value on a scale or not being able to hold a rod vertically. Each of these will introduce a small error to the measurement. Now that we know the sources of errors in our measurements, let's discuss the type of errors. There are actually only 2 error sources in survey measurements: systematic errors and random errors. Systematic errors follow mathematical and physical laws. Their magnitude and algebraic sign can be determined, and therefore systematic errors can be removed from survey measurements by applying corrections or using field procedures that remove the error, or applying corrections to the measurements after they are made. Examples include removing the effect of temperature from taping measurements by using a correction formula, or removing the effect of an instrumental error by measuring an angle twice with the telescope in both the direct and plunged positions. Random errors are the errors that remain after systematic errors are removed from the measurement. Remember that no measurement is exact. It will always contain some error. Random errors are caused by factors beyond the control of the surveyor and follow the laws of probability. The magnitudes and algebraic signs of random errors are a matter of chance. The errors tend to be small and compensating in nature, and while they cannot be eliminated from the measurements, with some experience, the surveyor can estimate their value. Our discussion of measurement analysis is a study of these random errors. There is another type of error that is really not an error at all, but still must be mentioned here. This is the blunder or mistake. These are personal in nature and include writing down the wrong measurement or writing down the measurement incorrectly. Transposition of figures is probably the most common mistake a surveyor makes. Mistakes can be detected by making repeated measurements of the same value. When a mistake is detected, the measurement should be repeated. One last area of confusion we need to clear up before we get to measurement analysis is the difference between accuracy and precision. The best way to define these two is to use the classical example of a bullseye. Suppose you take your gun to the shooting range for some practice. You aim very carefully at the bullseye, take a deep breath, exhale, and then take the 10 shots shown here. Your shots are very close together, but they miss the bullseye. Your shots are very precise, in other words, close together, but not very accurate. They miss the bullseye. Your gun has some type of aiming problem. This problem can be fixed, so it can be considered a systematic error. Now suppose you have your gun fixed and go back to the range. This time, you're not quite as careful with your aiming before you take your 10 shots. The result is shown here. The shots are scattered around the target, but are centered around the bullseye. These shots are not as precise as before, but are considered more accurate. As you have seen, precision does not necessarily equate with accuracy. You may tape a distance very carefully and get very precise results. But if you fail to take into account the tape is short by 5/100ths of a foot, you will not be accurate. The goal of the surveyor, and this is very important, is to always get accurate results with the precision necessary for the project at hand. Your precision does not have to be as high for, say, topo work as it does for boundary control work. Again, let me emphasize that your work must always be accurate, or you have wasted your time. But the precision can vary depending on the project at hand. This brings us to the study of error theory. Before we can begin looking at a series of measurements to define their precision and accuracy, all systematic errors and mistakes, or blunders, must be eliminated from the measurements. Remember that systematic errors have magnitudes and algebraic signs that can be determined and therefore can be removed from the measurements. Mistakes or blunders must be detected and removed, and then the measurement should be made again. Let's look at a group of measurements and begin our study of random errors. Shown here is a set of 12 measurements of the same angle. In other words, we've measured the angle 12 times. As you can see, the values for the individual measurements differ slightly. All systematic errors and mistakes have been eliminated. Our first task is to determine the most probable value for the angle. In surveying, we generally use the mean as the most probable value. The mean is defined as the summation of all the measurements divided by the number of measurements. In our example, the number of measurements would be 12. At this point, I would like for you to stop the tape and determine the mean of the 12 measurements. Since all the measurements have the same value for the degree and minute portion, I would suggest you work only with the seconds portion of the measurement. Let's look at the results of determining the mean. As you can see, I've added up the second portion of each measurement, and with the result being a value of 540. When I divide this number by the number of measurements, in this case 12, I get an answer of 45. The mean of this set of measurements is 56 degrees, 23 minutes, 45 seconds. This is the most probable value for the set of angles. Remember that the true value can never be actually determined. The mean is our best estimation of this value. Our next step is to determine the precision of the set of measurements. To determine the precision, we must first determine the residual for the 12 individual measurements. A residual is defined as the difference between the value of each individual measurement and the mean of all the measurements as shown by the formula. Residuals are theoretically identical to errors, except that the residual can be calculated and errors cannot. Take time now to determine the residual for each measurement in our example and note them in the column under the small r. Here is the result of calculating the residual for each measurement. For measurement number 1, the observed value minus the mean equals 0. For measurement number 2, the residual equals 1, and so on down the line. If you total the residuals for each measurement, the answer should be approximately 0. In our example, the sum actually is 0. This indicates that the residuals or errors are in fact compensating and tend to be small values. At this time, it's usually a good idea to create a histogram from the information we have calculated so far. A histogram gives us a graphical representation of the precision of our work. In the histogram, we plot the value of the residual, shown along the bottom line, versus the frequency of each value, here shown along the left side. The -2 residual occurs one time, the -1 value 3 times, and so on. When you connect the location of each value with a smooth curve, the result is the standard probability curve. This graphical representation will highlight any values that might contain a systematic error or a blunder that were not removed prior to determining the mean. These will appear as spikes or valleys in the histogram. If these are present, they should be removed and the mean and residuals recalculated. Steep-sided curves indicate high precision. The residuals are grouped closely together. Shallow-sided curves indicate low precision. The residuals are more spread out. After you have completed this course, you may want to take some survey data and determine the mean and residuals, and then plot the histogram to compare precisions. To accurately determine the precision of the data, we must next determine the standard deviation, or standard error as it's sometimes called, for our measurement data. Here is the formula for calculating the standard deviation. The standard deviation, or error, equals plus or minus the square root of the sum of the residuals squared divided by the number of measurements minus 1. The result is plus or minus because the algebraic sign of a random error cannot be determined. The sum of the residuals squared is determined by squaring each residual, then adding up the results. This formula is a standard formula used to determine the precision of any group of measurements and is developed from statistical analysis. Take time now to determine the standard deviation for the example. Let's see how you did. Here I've determined the residual squared for each residual. I've totaled these values and gotten 14. By inserting this value along with the number of measurements into the formula for standard deviation, I've come up with a value of plus or minus 1.13 seconds, which can be rounded to plus or minus 1 second. Remember that all random errors have a plus or minus value since the algebraic sign cannot be determined. The standard deviation establishes the limits within which measurements are expected to fall 68.3% of the time. Understand that this 68.3% value is a constant established by the laws of probability, and we will accept it without any further discussion, because if I tried to explain how it was determined, we'd be here for the next 3 weeks. Therefore, in our example of 12 measurements, it would be expected that 8 of the 12 measurements would fall within the range of 56 degrees, 23 minutes, 44 seconds, to 56 degrees, 23 minutes, 46 seconds, while 4 of the measurements would be outside the limits. In our example, 10 of the measurements actually fall within the plus or minus 1 second range. Another interpretation could be that if 1 or more measurements were made, it would have a 68.3% chance of falling within the standard deviation range. A third interpretation would be that the true value, and remember that we cannot actually measure the true value, has a 68.3% chance of falling within the standard deviation range. You should be able to see that the standard deviation is a comparison of the mean to the individual measurements that it was established from. By comparing the mean to the individual measurements, we have determined the precision of our measurements. This is the most important thing to remember about standard deviation. It is a measure of the precision of the measurement we are making. As a surveyor, you probably wouldn't want to tell your client that you're only 68.3% certain about the results of your measurements. A 90% or 95% level of confidence would be much better. You can determine different levels of confidence by multiplying the standard deviation by a constant that, again, has been determined by the laws of probability. Shown here are the 3 most common levels of confidence that a surveyor should be familiar with. The 50% error, or E sub 50, is the so-called probable error. It establishes the limits within which the measurement should fall 50% of the time. In other words, a measurement has the same chance of falling within the limits as it has falling outside the limits. The 50% error is calculated by multiplying the standard deviation by 0.6745. In the past, the 50% error was used extensively in the discussion of random error, but is seldomly used today. However, it does occasionally show up on the LS or LSIT exam. The 90% error, or E sub 90, establishes the limits within which the measurement should fall 90% of the time. It is calculated by multiplying the standard deviation by 1.6449. In our example, the 90% error would be plus or minus 1.13 seconds times 1.6449, which equals plus or minus 1.86 seconds, which is then rounded to plus or minus 2 seconds. Referring back to our example, you will see that all the residuals fall within this limit. The 90% error is the standard used today in the survey industry. Another statistical value that we should be aware of is the standard error of the mean. The mean, or most probable value, has some error with respect to the true value of a measurement. This difference is determined by calculating the standard error of the mean. In this formula, the standard deviation, or standard error, is divided by the square root of the number of measurements. Again, this is a plus or minus value, since the sign of a random error cannot be determined. If the standard deviation is not required, you can calculate the standard error of the mean directly from the measurements by taking the square root of the sum of the residuals squared divided by the number of measurements times the number of measurements minus 1. Of course, this is a plus or minus value. In our problem, the standard deviation, which is 1.13, is divided by the square root of the number of measurements and is equal to plus or minus 0.33 seconds. Since we are comparing the mean to the true value here, it can be said that the mean value in our example has a 68.3% chance of falling within plus or minus 0.33 seconds of the true value of the angle. By using the 90% error in the standard error of the mean equation, we will get the 90% standard error of the mean value. Comparing the mean to the true value is a measure of accuracy. Therefore, the most important thing to remember here is that the standard error of the mean is a measure of accuracy of the figure being measured. Again, I must emphasize that if any systematic error or mistake exists in the measurement data, then these calculations of the standard deviation and the standard error of the mean are invalid. So far, we have been discussing the error found in a single value that has been measured numerous times. Seldomly, if ever, is a survey project made up of a single measurement. Our projects are usually made up of numerous measurements of distance, direction, and elevation. Let's now see how the errors within the individual measurements propagate through a series of measurements. Sometimes a series of similar quantities, such as the angles of a traverse, are read with the same care. Each measurement will be in error by about the same amount. The total error in the sum of all measured quantities of such a series is called the error of the series and is designated by the E sub-series. If the error E is the same in each measurement, and there are n number of measurements, then the error in the series will be plus or minus E times the square root of n. Suppose that when a party chief and his chainmen use a 100-foot tape, there is a plus or minus 0.02 foot error from all the error sources. What would be the error if this team had to measure a 5,000-foot distance? In this case, the number of tape lengths in this 5,000-foot distance is 50, and the error of this series would be equal to plus or minus the error, which is 0.02 feet, times the square root of the number of measurements, which is 50. The answer would be plus or minus 0.14 feet. Using a similar technique for each of the 50 tape lengths in a 5,000-foot distance will produce an error of plus or minus 0.14 feet. This answer illustrates that random errors tend to be compensating. If each tape length definitely contained 0.02 feet of error, then the total error in 5,000 feet would be 1 foot. This is the product of 0.02 times the 50 lengths. However, in random errors, errors have a plus or minus value, and therefore they tend to compensate over the 5,000-foot distance. Therefore, the error in the 5,000-foot distance is less than the absolute maximum error of 1 foot, and in this case is plus or minus 0.14 feet. One other point needs to be made here. If you want to determine the precision of your 5,000-foot measurement, then you use the standard deviation, or 90% error, for the value of E in the equation. If you want to determine the accuracy of your 5,000-foot distance, then you should use the standard error of the mean, or the 90% standard error, for the value of E. It is important to identify what it is you're trying to determine, either precision or accuracy, before you do your calculations, so that the correct formulas and procedures are used. A special type of error in a series is the error found in electronic distance measurement, or EDM measurement. As you all are aware, EDMs are used for most distant measurements today. We'll discuss the specifics of EDMs a little later on. Right now, we'll discuss the error found in EDM measurements. Here we have the formula for determining the error in an EDM measurement. In the specifications that were sent with the EDM, there is a value given for the accuracy of the instrument. For the geodometer 410, this value is plus or minus 5 millimeters, which is equal to 0.016 feet, plus 5 parts per million. This equation indicates that there is an error of plus or minus 5 millimeters in every measurement, regardless of the length of the line, plus an additional error which is dependent on the length of the line. This additional error is a proportion to the value of 5 parts in a million. What this means is that if we could measure 1 million feet with this EDM, it would create a 5-foot error. By proportioning this ratio to the length of the line being measured, we can determine the total error. In this example shown here, we have measured a line 1 mile, or 5,280 feet long, with an EDM. The total error for this line would be equal to the plus or minus 0.016 foot error found in every measurement, plus 5 parts times the ratio of 5,280 to 1 million. This proportion is equal to 0.026 feet. The total error would therefore be plus or minus 0.016 feet plus 0.026 feet, which equals plus or minus 0.042 feet for the 1 mile line. This error is a standard error of the mean value and is therefore a measure of accuracy. The next type of error propagation that you should be familiar with is the error in a sum. In this case, we are determining the error of a group of measurements that do not have the same error for each measurement. Our formula shows that the error in a sum is equal to plus or minus the square root of the error in measurement A squared plus the error in measurement B squared plus the error in measurement C squared, etc. Suppose that we measure each angle in a triangle under varying conditions. The error in angle A is plus or minus 10 seconds. The error in angle B is plus or minus 2 seconds. And the error in angle C is plus or minus 5 seconds. The total error for the angles in this triangle is equal to plus or minus the square root of 10 squared plus 2 squared plus 5 squared, which is equal to plus or minus 11.4 seconds. This answer demonstrates that the total error in a group of measurements having varying errors is only as strong as its weakest link, or angle in this case. Measuring the other two angles more precisely than the weakest angle does not improve the overall precision of the sum of the errors. You now have the tools necessary to begin determining the error in most of your survey measurements. Take time now and try to solve the point location problem in your workbook. Let's see how you did in determining the positional error in point C. First, we'll determine the error in the distance measurement. We measured a distance of 4,350 feet using an EDM that had an accuracy of plus or minus 0.016 feet plus 5 parts per million. Substituting this data into the formula for EDM measurement, we get plus or minus 0.016 feet plus 5 times the ratio of 4,350 over 1 million, which works out to be plus or minus 0.038 feet. Now, solving for the error in the angle, we can use simple trigonometry. The linear error value is equal to the tangent of 10 seconds, which is the error in our angle, times the length of the line, 4,350 feet, which equals plus or minus 0.211 feet. Remember that the tangent of an angle is equal to the opposite side, which is the error amount, divided by the adjacent side, which is the length of the line. By rearranging this formula, we get the error at point C equals the tangent of the angular error times the distance of the line. Now, since we have two error sources with different values, we can use the error in a sum to determine the positional error of point C with respect to point A. This is equal to plus or minus the square root of 0.038 squared plus 0.211 squared, which equals plus or minus 0.214 feet. Remember that if we want to determine the precision of our measurements from A to C, then the angular error and distance error must be the standard deviation, or 90% error. If we want to determine the accuracy of point C, then the angular error and the distance error must be the standard error of the mean, or the 90% error of the mean. Let's take this idea of error propagation one step farther. You can use the study of errors to predetermine the outcome of a survey. Take time now to try the estimated traverse closure problem in your workbook. In this problem, we know the positional error for each side of the traverse, and we can therefore determine the positional error for the entire traverse, or as it's more commonly known, the error of closure. Here I have calculated the positional error for each side of the traverse based on the data given. Since each of the values is different, we must use the error of a sum to calculate the total error for the traverse. This is equal to plus or minus the square root of 0.212 squared plus 0.176 squared plus 0.144 squared plus 0.230 squared, which is equal to plus or minus 0.387 feet. This would be the expected closure of the traverse based on the data given. If you calculate the actual error of closure, it is 0.311 feet. Since the actual closure is better than the estimated closure, the work was done correctly, and there probably are no mistakes in the field data. You can also use this estimated error to determine the equipment and procedures necessary to have a survey conform to a classification of accuracy. In your workbook, you'll find the classifications of accuracy from the Caltrans Survey Manual. In Table 4-04-B, there is an accuracy requirement for second-order modified traverse that states that the positional closure, after azimuth adjustment, will not exceed 1.67 feet times the square root of the length of the traverse in miles, or 1 part in 10,000, whichever is smaller. If you are planning a traverse that is 2 miles long, then by the requirements mentioned above, the survey must have an error of closure of not greater than 1.06 feet. By knowing this, and the approximate dimensions of the sides of the traverse, you can determine the equipment and procedures necessary to achieve this requirement. For a complete study of this subject of error propagation and estimating survey requirements, get a copy of Ben Buckner's book, Survey Measurements and Their Analysis, which is noted in the bibliography in your workbook. The last topic we need to touch on before we move on to different types of survey measurements is the different types of adjustments we can use to ensure that our surveys are mathematically correct. In some types of surveys, the sum of several measurements must equal a fixed value. For example, the sum of the interior angles of a triangle has to total 180 degrees. In practice, therefore, the measured angles of a triangle are adjusted to make them add up to the required total. Correspondingly, distances may be altered slightly to meet certain requirements. In making these adjustments, the principles of probability are most important. The most common type of survey adjustments are the proportional or linear adjustment. This is an adjustment used in simple level circuits and traverses. In adjusting the survey data, the adjustment is simply a proportion of the total error total distance ratio. For example, if a simple level circuit has a closure error of 0.25 feet and is 5 miles long, then a benchmark at the 1 mile mark will get 1/5 of the adjustment, or 0.05 feet. The compass rule and transit rule adjustments used in the adjustment of traverse data are also proportional adjustments. Level adjustments and traverse adjustments are dealt with in detail in their appropriate unit of this review course. The most important thing to remember about these adjustments is that the errors are considered to be equal for each leg of the level circuit or traverse. There cannot be any other error considerations with proportional or linear adjustments. It is evident that some measurements are more precise than others because of better equipment, improved techniques, and superior field conditions. In this situation, it is better to assign relative weights to the individual measurements. When this is done, the stronger measurements receive the least amount of adjustment, while the weaker measurements receive the greater amount of adjustments. This is the theory behind using weighted means and least squares adjustment. Least squares is an adjustment where the sum of the residuals squared for the set of measurements is minimized. It is a statistical analysis where each measurement is weighted and all measurements are adjusted simultaneously. The result is considered a superior adjustment to proportional or linear adjustments. The study of weighted means and least squares is a class all by itself, and we won't go any farther here. It should be realized, however, that any adjustment beyond the very simplest should be done by a least squares adjustment. With the new least squares adjustment packages on the market today, which make the input and adjustment relatively simple, least squares adjustment is becoming a very common method of adjustment of almost all survey measurements. It is time now to begin our study of the different types of measurements we have in surveying. We'll begin our study of survey measurements with that of distance. To review, the three types of distances that we are interested in are horizontal distances, shown here by the lines A to O, B to O, and A to B, vertical distances, shown here by the line AC, and slope distances, shown here by line OC. Distance measurement is the basis of all surveying. In plane surveying, the distance between 2 points means the horizontal distance. If the points are at different elevations, the distance is the horizontal length between the two vertical lines of the points. The horizontal distance that relates to the slope distance OC is OA measured to the vertical line AC. There are several different methods of measuring horizontal distances. These methods include pacing, odometer readings, optical rangefinders, tachymetry, better known here as stadia, subtense bars, taping, and electronic distance measurement. We'll discuss taping and EDM measurements in detail in a few minutes. Let's briefly discuss the others now. Pacing distances are sufficiently accurate for many purposes in surveying. Determining the general location of a monument from a found monument is a common example. Once you're in the general area of the monument, you can use a metal detector or similar device to actually locate the monument. Pacing can also be used to detect blunders in tape distances. Pacing is simply counting the number of steps or paces in a required distance. Before this is done, you must determine the length of your pace or the number of paces per a certain distance, like 100 feet, by walking with natural steps back and forth several times over a level measured course. With practice, you should be able to pace within a foot over a distance of 100 feet if the terrain is open and reasonably level. An odometer converts the number of revolutions of a wheel of known circumference to a distance. The odometer in your car is suitable for some preliminary work in route location work. More common is the measuring wheel that is pushed by hand and the distance then read on the odometer connected to the wheel. Accuracy with this type of device on level ground is approximately 2 feet per 100 feet. Optical rangefinders operate on the same principle as the rangefinder in your single lens reflex camera. The operator looks through the lens and adjusts the focus until a distance object viewed is focused in coincidence, whereupon a distance reading is obtained. Accuracy is about 2 feet per 100 feet up to a distance of 1,000 feet. Beyond this distance, the accuracy drops rapidly. Tachymetry, or stadia, as it is more commonly known, is a surveying method used to quickly determine the horizontal distance to and the elevation of a point. Stadia measurements are obtained by sighting through a telescope equipped with 2 or more horizontal crosshairs, commonly called stadia hairs, set at a known spacing. In the United States, the crosshairs are usually set at a ratio of 1 to 100. When looking at a leveling rod held vertically at a distance of 100 feet from the instrument, the distance between the 2 stadia crosshairs will be 1 foot. When the distance between the 2 stadia hairs is 1.59 feet, the rod is 159 feet away. Stadia is still used in many parts of the United States for doing topographic surveying. Our field crews at SOMAS are all trained in stadia just in case one of their electronic total stations fails on a critical topo job that is far away from the office. If this should happen, they can use the backup theodolite they carry and use stadia to continue until a replacement instrument arrives. Stadia is accurate to 1 foot in 500 feet for horizontal measurement. The subtense bar can be used along with a precise theodolite to determine distance. The bar is usually made of invar, and targets at the end of the bar are a known distance apart, usually 2 meters. By setting the subtense bar on a tripod at one end of a line and measuring the angle subtended by the bar with a theodolite at the other end of the line, the horizontal distance can be computed by trigonometry. An accuracy of 1 foot in 3,000 feet can be easily obtained with this setup. The subtense bar method of distance measurement was often used in the past to obtain distances over inaccessible courses, for example, over bodies of water. EDM devices have now almost totally replaced this procedure. Before we get into our study of tape distances, let's take a break here and get something cold to drink. I'll see you in about 10 minutes.